Hello everyone and welcome back to PC Retro Programmer. We're on a quest to draw ellipses on very early PC hardware, in fact the earliest hardware. And we don't want to just draw standard ellipses which are aligned with the horizontal and vertical axes of the screen, but general ellipses that are rotated at any angle. We've actually made a lot of progress on that in this series so far. We figured out that the best way to do it will be to emulate what we did for the standard ellipse. And that is to break the ellipse up into 8 arcs. And basically these arcs will go from points on the ellipse where the ellipse starts to go horizontal or vertical or at an angle of 45 degrees, where the curve is going at those angles. So that marks out 8 points on the ellipse that will be the starting points of these 8 arcs that we have to draw. And in a previous video we already figured out the coordinates of all 8 of these points. You can see there's 4 sets of values here, and there's 2 in each. That gives 8 points. And they're all written in terms of constants a, b, c, and f. And this is where they come from. So this is the equation for a general ellipse here. You can see those constants a, b, c, and f. Now the only problem with this is if I give you some random constants a, b, c, and f, you have no idea which ellipse that is going to be. It's a bit hard to visualize. It'd be much nicer if everything was written in terms of, let's say, the width of the ellipse, the height of the ellipse, and the rotation angle theta. So actually what I'd really like is for it to be written in terms of the semi-major and semi-minor axes, r and s, and the rotation angle theta. So we'd have r, s, and theta. Those would be much nicer constants to use because that's something I can actually visualize then. So believe it or not, I've actually done that already in a previous video, and you saw it when I did this animation here. I figured out what the A, B, C values would have to be in terms of these 3 constants. And you can see that as I change the angle theta, the ellipse rotates around. And so we actually already have expressions for at least A, B, and C in terms of these 3 values that I want, r, s, and theta. And the easy way to do that is what I explained in the video, to basically just rotate the coordinates x, y using a rotation. You could just look up the formula for a rotational line. So I already went through that, but I thought it would be fun in today's video to start off by showing how someone else did it. There's this guy called Da Silva who in the late 1980s wrote a paper on how to draw ellipses, and it seems that he's made exactly the same choices that we have. I've actually implemented his algorithm before, but on much more advanced hardware. And there are some issues with the algorithm, but it's pretty good. And so far we seem to have been following pretty much his line of thought. But he has a really nice way of computing these values, A, B, C, and he calls it D rather than F. And basically it relies on some facts about the ellipse that were known for thousands of years, in fact. So I thought it'd be really nice to show how he did it. And then we'll have 2 different ways of getting to the same result. So Da Silva's basic observation has to do with what are known as the foci of the ellipse, or focus points if you like. So I drew them here and here on this ellipse, and basically the ellipse is defined to be all of the points such that the sum of the distances to the foci remains constant. So if I take this distance and add this distance, I'll get some value. And if I pick some other point on the ellipse, let's just take this one here, and take the sum of its distances to the foci, so this length and this length, and add those together, I'll get the same thing. And I can do that for any point on the ellipse. And this is actually how the ancient Greeks defined ellipses. They didn't have coordinate geometry like we do. They did everything in terms of triangles and lengths. So basically, what Da Silva does is he says, what I want to do is figure out where this focus point actually is. What's the coordinates of the focus point here? So we've got an ellipse, and we're going to start off with semi-major radius r, so this is the long radius here, and semi-minor radius s, this will be the short one here, and we'll just call this distance to the focus point c. And it turns out that we can actually work out what this distance is in terms of r and s just using Pythagoras' theorem, which is amazing. So Pythagoras' theorem is another theorem that the ancient Greeks knew, and basically it says that if I have a right angle triangle, let's take this one here for example, then if I sum the squares of the two sides, so if I took s squared and c squared and added them together, that would give me the square of this side length. So it's a pretty basic theorem, and that's all you actually need here. So the idea is that basically we take a look at this focus point here in two different ways. So first of all, we take a look at it with respect to this point on the ellipse. So let's just sum up the distances of this point to the two foci points. So obviously the distance to this focus is r minus c, and the distance to this focus is c plus r minus c, and if you add those together you get 2r. So I've just put that on one side of the equation here, and that distance, the sum of these two distances here, has to be the same as the sum of the distances from this point to the two foci. And those distances will actually be the same since the ellipse is symmetric. So I just need to figure out what one of these distances is. And as I said, that's given to us by Pythagoras' theorem. This distance here is the square root of the sum of the other two squares. And so we're going to have that twice, once for this side and once for this side. And so on the other side of my equation, I've got 2 times that square root. Now it turns out that if I just divide by 2 on both sides and square both sides of this equation, I get that r squared is c squared plus s squared. And you can see it's pretty easy to rearrange this to get c in terms of r and s. So that's how De Silva computes, without actually really using any coordinate geometry per se, how far along this focus is. Now the thing is, if I rotate this ellipse, this focus will stay exactly the same distance from the origin. So that length's not going to change, and nor is the length r and the length s. Just rotating an ellipse won't change any of those values. So it means that even for the rotated ellipse, I still know the distance of the focus from the origin. So the question is now, can I figure out what the coordinates of the focus would be in the rotated ellipse? So let's take a look at that. So it turns out that this is actually really easy to do. So what I've done in this diagram here is I threw away all the information that we don't need. The only thing we actually need now is this distance to the focus point, this green line here, which has distance c. And we know that after we rotate this line around the origin by an angle theta, we'll end up with another line here, which I've also drawn in green, which also has length c. Just rotating something doesn't change its length. And so basically that point will be somewhere on a circle of radius c. And so that's what I've actually drawn here. And the question that we want an answer to is, what are the coordinates of this point after I do the rotation? So maybe you already know this, but actually the cosine and sine functions are actually defined to give us these coordinates here. So if I have a circle of radius c, and I pick a point which is angle theta around, then the coordinates, x and y coordinates, which we'll call xf and yf here, so x focus and y focus, these coordinates are defined to be c times cos theta and c times sine theta. That's actually how you define the cosine and sine functions. And so that's basically all there is to it. So that gives De Silva a way of actually figuring out the coordinates of the rotated focus point on the ellipse. And now all that remains from here is for him to figure out some equations to give those constant values, a, b, c, and f, that we talked about, in terms of r, s, and c. And basically given these coordinates of the rotated focus point. You don't need very much to do this. I'm not going to go through the derivation, but the only thing you actually need is the equation for the distance between 2 points in the plane. That's important because, of course, the ellipse that we're trying to draw is defined to be the set of points such that the sum of the distances to the foci is constant. So you need to be able to compute distances between points. But once you have that formula for the distance between any 2 points, it's a pretty straightforward exercise in algebra, just a bit of a boring one, which is why I'm not going to show it, to actually figure out the equation of the rotated ellipse in terms of rs and these points xf and yf, which we now know how to compute. So that's basically all there is to it. So let me show you what De Silva came up with in his paper. So here's the start of where De Silva actually gives his algorithm for drawing a general ellipse. It's written in a kind of Pascal syntax. So I won't go into this in any great detail here. We're only interested in the first few lines here. So basically he starts off with the semi-major radius, which he calls A, we've been calling that R, and the semi-minor radius B, and we've been calling that S. And the first thing that he does is compute this distance to the focal point that we talked about, and this is exactly the equation that we came up with. So then he computes the coordinates of the rotated focal point, xf and yf, and that's exactly what we came up with as well. And so now he gives a set of equations, in fact even better than that, he gives a set of operations that we can perform, just given these values, to compute a, b, c, and what we've been calling f, he calls it d here. So that will give us the 4 constants for the ellipse that has semi-major radius A, semi-minor radius B, and rotation by this angle theta here. And so now we know how to compute A, B, C, and D in terms of those. So what I'm going to do for the final part of this video is I'm going to actually show an implementation in the Julia language of these first few lines of De Silva's paper. It's obviously going to be pretty trivial. And then we're going to use the pixel drawing code that we set up in the previous video using the SDL library to actually draw all of the 8 points that are the starting points for our arcs that we have to draw. And actually this is precisely what he's computing down here. Unfortunately there are some errors in what he writes, so hopefully we did it correctly in the previous video where I actually looked at what those points are. But we're going to compute those and actually draw them and then do some animation and rotate those 8 points and see if anything goes wrong. Well, I've gone ahead and coded all this up, and let's take a look at it. So the first thing that I did is I changed my filled rectangle routine. So I realized that in order to draw a filled rectangle on SDL, it seems that you have to draw 2 triangles, what they call trigons. So I've gone ahead and made a draw filled rect routine that I can call, and I changed my draw pixel routine to call that. And I also made a clear function which will just blank the entire screen by drawing a big filled rectangle with color 0. I wasn't able to get the renderer clear function to work for some reason, so that's why I've done it that way. it's really not that important that we get things done the exact precise STL way. So the most important routine here, of course, is the draw ellipse routine, and this one has three parameters, R and S, and our rotation angle. Now I want the rotation angle to be in floating point, and the way to do floating point in Julia is with the float 64 type. So this is just a double precision floating point number. Now obviously we're not going to use floating point in our assembly program. We'll probably use some kind of fixed point, but I want to do the calculations as precisely as possible here with a pretty high precision and with actual floating point, so that we can rule out that the precision is part of the issue if we run into troubles. So from here, basically, all of the lines that you can see are pretty much exactly what De Silva has in his paper, and I've just called it F instead of D, and I've used R and S instead of A and B, but otherwise it's exactly the formulas from De Silva's paper. I just wanted to check that A was actually bigger than 0, and it seems like it always is, so that's no problem. Although I do notice in this algorithm that R has to be bigger than S, since you take the square root of the difference, and that would be a complex number if this was less than 0. So that's one restriction which I hadn't really noticed. Now here's the trickery. So what I want to do is I want to make it so that the values A, B and C, and in fact the largest value that I can see that we'll actually use in the formula itself, in the algorithm that De Silva provides, will be this value here. It'll actually be twice this, so it'll be 2A plus twice the absolute value of B plus twice C. And I want that value, once we've scaled everything, to fit into a 16-bit integer. In fact, I want it to fit into a signed 16-bit integer, and so I don't want it to exceed 2 to the power of 15. And because I'm actually going to be rounding these values in the end, there could also be some other issues here as well. So I've just subtracted a little bit off here so that the value will be a little bit less than 2 to the 15. And so this is a scaling factor that I would have to multiply everything by to ensure that this sum, this largest value that appears in the algorithm, would be less than 2 to the 15, just a little bit less. Now, the other thing I want is the f value to be less than 2 to the power of 31, because I want that to fit into a signed 32-bit integer. And f is actually negative, so I have to put a negative sign there. And so this one here is the scaling factor that I would have to use in order to ensure that f is less than 2 to the 31. And then basically I'm going to have to use one or the other of these scaling factors, and I need to use the smallest one so that both of these conditions are met. And so this is what this is. This is our final scaling factor. And then basically I can now compute A, B, C and F by rounding those values after multiplying them by the scaling factor. So that now gives us A, B, C and F to the highest precision that we can really get away with, such that A, B and C will fit in 16-bit integers and F will fit in a 32-bit integer. Now here in Julia, I'm just going to do everything in 32-bit integers because it'll just make it a little bit easier to fiddle around with. But here I'm actually casting them to what I think the sizes should be in the final implementation, just to make sure they actually do fit. But I'm going to use these values in the Julia implementation, not the test values. The other value that we have in our formulas is this discriminant value here, this b squared minus 4ac, so I compute that. And then most of the rest of this here is pretty much just how De Silva computes these values. I made a few changes here. You'll see why in a moment. I'll show you what happens if I use De Silva's formulas. It doesn't quite work. Actually I still haven't quite got this 100% right, but it's a lot closer now, and it should be easy enough to fiddle around to get it perfect. But basically these just compute the coordinates of 4 of the points. So the north point, so the one at the top of the ellipse, the northeast point at top right, northwest at top left, and there's also the east point, so the one on the right of the ellipse. So those are the 4 points, and of course the other 4 points would just be reflections of these about the axes, so we don't need to actually bother computing those. And of course I'm going to round these values to integers, and those are the points that are the starting points for 4 of our arcs on our ellipse. And then the final piece of code, of course, just draws those 4 pixels and their reflections. You can see that I have XH, minus XH, YH, and minus YH. And the 160, 100 is just the center of the screen. It's just to move the ellipse into the center of the screen. So this is pretty straightforward. So it's just going to draw those 8 points. It won't draw anything else just yet. And in the main program, I just now have an R, an S, and a theta value. And now when I press certain keys on the keyboard, I can change these R and S values, or I can change the rotation angle theta. So I've made it so that you can do it in steps of 1/512th of a full circle. So that's a fairly small rotation step, and basically if you press keys you should be able to rotate all the way around. The rest of it's pretty much the same. I did add a clear renderer thing in here just to blank the screen between each set of 8 points that we draw so we can see them move. And so let's take a look and see what happens. Well, here's what happens when we compute the points the way De Silva recommends. I'll just make the ellipse a little bit wider here, and we'll make it a little bit higher as well. And already you can see a problem. There seem to be 2 points missing. The one in the northeast and southwest seem to be not there. And if I start rotating, points just suddenly start going all over the place. So there's something clearly wrong here, and in fact if you look at De Silva's formulas, one of the points, the one on the left hand side, has the wrong sign for sure, and there are some other errors as well. Now I actually previously implemented this algorithm on more advanced hardware, and I corrected some of these issues, so let's take a look at the result with those corrections. So I've gone ahead and made those changes, and this is the result. So I make the ellipse wider, all the points are there now, and if I start rotating, I can get from 0 to 45 degrees, and it more or less stays in the shape that you'd expect. Once I start going beyond about 45 degrees, around about this point here, maybe here, it starts to widen out way too much. There's something not quite right there. And this is due to the sign of one of those coordinates being incorrect. The signs need to change at certain points, and unfortunately it looks like my formulas don't quite work for all values either. So that's one problem. Another issue is that if I make the ellipse very narrow, and here by very narrow I mean sort of 3 pixels wide, and try to change the size of the ellipse, then I can press the key multiple times and nothing happens. And that's obviously because the A, B, C, and F values aren't actually changing for any of the values that I'm inputting. And then all of a sudden it will just jump to the next value. And so this is an indication that we have a precision problem. So even with all of that care taken with the precision there, it seems like 32 bits is not enough for the F value when you have a very, very thin ellipse. So whether or not that's going to be a problem, or whether we just don't allow really thin ellipses, well, that'll remain to be seen. But for the time being, at least we can see there are some issues here that need to be resolved. So that's what we'll do for the next video. We'll try and sort some of this out and figure out these issues before we move on to actually plotting the points to join up the different arcs. But I think we've made some progress here. We've spotted some problems, and we've actually got it so that it does indeed draw some of the points on the ellipse. And just to finish off with a little bit of fun, I took out the code that blanks the screen between drawing each set of 8 points. So it'll leave trails now. So let's see what this looks like. So I can just press random keys and I can get all sorts of weird shapes appearing on the screen. So it looks like it should probably draw things in ellipses, and you can see that every now and again it deviates from that, and that's actually where the errors are in the code. But you can see that you can get some pretty fun shapes out of this. I just thought that was interesting to finish off with.